Hello and welcome to this MPLS training session. My name is David and I'm a network engineer. I specialize in service provider networks, backbone infrastructure, and technologies such as MPLS, BGP, and IP routing. Now, as you can see from your screen, I've just given you a brief bio about myself and basically how you can be able to reach me or us. This video is done in collaboration with the LiFi Technologies. If you want to check them out, this is if you want to check them out, this is their YouTube channel. Please go and check. We have very many videos that might be of interest to you. Now, this training is part of a broader MPLS video series that I will be producing, where we will cover MPLS concepts and configurations step by step, starting from the fundamentals all the way to advanced implementations. Now, the practical focus will be on Huawei and Cisco devices, specifically Cisco routers. Now, we will take hands-on approach, building an MPLS network from scratch and exploring configurations on the said Cisco and Huawei devices, which, as we know, are widely used in service provider environments and large-scale enterprises today. In my day-to-day role, I work extensively with MPLS-based networks, handling real-world scenarios such as provisioning, troubleshooting, and ensuring network stability. So throughout this training, I will also be sharing practical insights that are drawn from live operational environments. The objective of this session is to give you a solid understanding of MPLS, including what MPLS is and why it is used. So we'll cover things like core components, which include provider edge, provider and customer edge devices. We'll get to see how label switching works and how MPLS enables services such as L2 VPN and L3 VPN. In other words, we'll be able to see the application of MPLS, specifically the two types of VPNs, that is L2 and L3 VPN. So, as you might be aware by now, MPLS is a key technology in modern networks. Modern meaning there's a traditional way of doing things or how things were done traditionally before MPLS was invented in 1997. So MPLS enables efficient, scalable, and predictable traffic forwarding, making it critical for enterprise services, cloud connectivity, and large-scale ISP backbones or enterprises. So in this session, we will start with core concepts and gradually build up towards practical understanding. Now, in the subsequent videos, we will move into full configuration and real-world scenario deployment of MPLS. So with that very brief introduction, let's get started by first understanding what MPLS is and how it differs from traditional IP routing. But before we dive in, a few things that you need to know or you need to have to understand this particular training is that you need to have a basic understanding of subnetting, specifically for IPv4, because we'll be doing we'll be dealing with IPv4 throughout this course, not IPv6. And then secondly, I would encourage you to have a basic understanding of IP routing, specifically OSPF and ISIS for IGPs and BGP for exterior gateway protocol. The reason as to why these three are important is because they work together or they work hand in hand to be able to enable networks to function as they're designed out there. So these three are very important. So and for MPLS configuration, we will go with ISIS, but you can also pick OSPF but in this case, we will be dealing with ISIS. So for BGP, we will get to use it when we will be configuring L3 VPN, specifically for something we call PE and CE peering. We will use normal BGP, specifically IPv4 address family. And then we will also have MP-BGP, where PE will be able to peer, PEs will be able to peer with each other. And here we'll use the VPN v4 address family, which will enable PE to be able to transport customer routes with each other. So I'm going ahead of myself here, but basically that's what we'll be able to cover. So stay with me until the end. And lastly, what you need to do is you need to have a basic understanding of MPLS. The reason as to why I'm saying you need to have a basic understanding of MPLS is because in this series of videos, we will not be deep diving into the theory part of MPLS. This is purely a lab session where we'll have various sessions of configuration of MPLS. Therefore, for you to be able to understand what we are doing, you need to have a basic understanding of MPLS operations, how it works. But not to worry, before we go there, this first video is just to give us a brief understanding or to lay the foundation of MPLS before we can log into the virtual environment and do the configuration from scratch. So moving on, let's now discuss about MPLS. Let's first of all define what MPLS is. So MPLS stands for multi-protocol label switching in full, and it's a networking technique used by service providers and large-scale enterprises to forward traffic faster and more efficiently using labels instead of IP lookups. So the IP lookups is the traditional way of doing things, where a packet arrives at a router. Before it goes to its destination, this router here will have to do an IP lookup in its global routing table to determine or to establish which is the best path to the destination. Now, that IP lookup is somehow extensive, and it's not efficient because it's not fast. Imagine the global routing table has to be analyzed for you to pick the best path, which in this case is an IDP, the established best path. So if you have OSPF or BGP running in your network, and they both have a route to the destination, what will happen is the router has to determine determine which of the two paths to use, and so that particular process is actually very extensive, as opposed to just using labels. So a prefix a prefix is assigned a label, and this is the label that you use when you are forwarding packets from one node to the other. So it makes it very efficient. We can think of MPLS as an efficient technology for managing network traffic flow. Next, let's now have a high level overview of what features MPLS has. Number one, we have high performance packet forwarding. As you said, we're not doing the normal traditional IP routing. We're basically using labels, and what that is able to do for us is that we are avoiding complex IP routing lookups whenever we are sending traffic from the source to the destination. Another feature of MPLS is that it's normally referred to a layer 2.5 technology because it sits right in between layer 2 and layer 3. For if you remember your OSI model basics, level 1 all the way to level 7. So we have level 2 and level 3. So level 2 is the data link layer, and level 3 is the network layer. So MPLS sits between, and the reason as to why it does that is because it combines the features of both data link and network layers. Then OSPF has multi-protocol support, just from the word multi-protocol, because we said it stands for multi-protocol label switching. So it has multi-protocol support. It means it can work with just about any layer 2 or layer 3 technology out there, which makes it very powerful, irrespective of whether you are using Ethernet frames or whether you're using ATM, or P2 PPP. It really does, or SDH. It really does not care what, for example, your layer 2 type is, or infrastructure. It will work with them regardless. So if point A uses an Ethernet, then point B uses another technology, a layer 2 technology, MPLS will still work because it will support that particular protocol. Now, it also has advanced features like support for VPNs. VPN stands for Virtual Private Networks, specifically L2 and L3 VPN. Of course, what you also get with the traffic, what you get with the MPLS is also traffic engineering and quality of service. And this particular features, enhance network stability and performance. So this is an overview of MPLS overview, basically the features or characteristics of MPLS. And moving forward, now let's talk about what exactly MPLS is. You realize that a lot of these things are actually repeated in different contexts, but they are designed to enable you have a better understanding of what MPLS is before we move into our lab and start configurations. So we said MPLS uses label to forward traffic. So it's label-based forwarding. It uses a short fixed length label to forward packets, simplifying routing decisions at each node. And then another thing that is normally associated with the MPLS is label switched path, or LSP for short. It's a predetermined route that packets that traffic is able to use from the source to the destination. For example, if we could use our topology on our right, now these two customers in blue belong to one company, for example. From the legend here, let's call the company Bravo, and then the one in green, these ones here, belong to Alpha. So let's say that company Bravo in this other geographical location wants to communicate. Maybe this is Uganda. I'm in Kenya, so let me use Kenya. I'm in Africa, so let me use African countries for better understanding. This is Kenya, for example. So if I want to communicate in Uganda, I want to communicate with my branch or my other offices in Kenya. Therefore, my traffic will either use this path to the destination, and probably maybe the return traffic will be able to use this other path to my destination again. So basically, the ones that I'm drawing in pink and blue is what we call label switched path. Then within MPLS, we've already discussed about traffic engineering and VPNs in our previous slide, but MPLS enables traffic optimization and supports VPNs for secure and isolated communication. Now let me explain. As you can see, this subnet here is the same as this subnet. Then this subnet is the same as this subnet, but customers are different. So what enables you to have customer isolation is MPLS VPN, specifically L3 VPN. That is what enables you to have that particular isolated communication. And basically, this customer cannot communicate to this customer unless specifically or explicitly instructed to by what we call route leaking. You can leak routes into this VRF or this customer and vice versa. So that is what you get with MPLS, the support for traffic engineering and L3 VPNs. We'll discuss about its topology as we move on, so just bear with me. So let's talk about, I think was first there, so why MPLS and what terminologies we have. So basically, these are the benefits of MPLS. Quickly, we already said that it's faster compared to IP routing, compared to traditional IP routing. Therefore, uh, one benefit of MPLS would be faster packet forwarding. And here, MPLS uses labels instead of IP lookups, enabling routers to forward packets faster and reduce latency. And then, of course, there's the traffic engineering. MPLS allows you to explicitly uh, MPLS allows explicit routing paths, improving bandwidth usage and preventing congestion in networks. We'll discuss about traffic engineering when we are doing the lab, so for better understanding. And so again, I encourage you to stay with me until the end of this MPLS video series. VPN support, we already said about L2, L3 VPNs. We also have L2 VPNs support that is the benefit you get when you use MPLS. Again, we will discuss this because our lab will have L3 VPN and L2 VPN configuration. Specifically for L2 VPN, we'll have to do for L2 VPN, we will do virtual private wired services instead of VPLS. These are the two common types of L2 VPN. So we'll do virtual private wired service basically, where we'll have our device here go through our service provider environment and then come out this other end for communication. So this IP address here, this IP address here will belong to the same subnet. For example, 10.1.1.0/24, for example. So that's what we'll be able to configure. But let me not go ahead of myself and spare this for a later video where we have the configuration. So when we do the lab, we'll have a better understanding for it. Of course, another thing about MPLS is that it enables support for quality of service. We'll be able to discuss about MPLS IP header, which um, has a segment, or it divided into four. We have the value, we have the traffic class, we have the bottom of the stack, and we have the TTL value, the TTL section. So QoS there is under the traffic class. So which enables MPLS to prioritize critical traffic such as voice and video to ensure reliable and high quality communication. The next, so key terminologies. Key terminology is where you need to pay attention. Key terminologies. We'll look at terminologies based on our service provider environment, SP. So when you talk about service, when you look at the key terminologies based on service provider network, then we get to have two, not two. We get to have three device roles. Number one, we have the provider edge, and then we have the P devices, and then we have the C devices. So provider edge routers add or remove labels. Provider routers swap labels. Customer edge routers do not handle MPLS directly, which means they are unaware of any MPLS configuration. So let's talk about this for a second. Let's take more time to understand these terminologies. Now, before going to terminology, let's just do the MPLS label. So the labels are fixed length identifiers that are used to forward packets through the MPLS network efficiently. And here, it is a 20-bit number and it's fixed. So this is another benefit, because if it's fixed, then it makes packet switching faster and efficient. Then we discuss about a label switched path. Basically, LSPs define predetermined paths that packets follow from ingress to egress routers in MPLS networks. I said if this customer want to communicate to this other branch, then they could either use this path, or if this is broken, then they could utilize this other path. So that is what we call LSP. Okay, so now let's talk about these router roles. So the provider edge devices connect to the customers directly, as you can see. That's their main aim. And then, of course, they also connect to provider devices, or in some designs, you could get that we have another PE, therefore they connect to each other. So key things to note there is a provider edge device can either communicate can either connect to a provider router, or it can connect to another PE router or PE device. But really, one of the most fundamental role of a provider edge device is that it connects to the customer edge device. And another role is that it adds and removes labels, as we'll be able to see as we move on with this particular training. Another device is now the provider. So these ones sit inside the MPLS core. So whatever I'm highlighting here, these are now the 4 devices here are the provider routers, or the core routers. They only connect to each other, and they connect to provider edge device. They do not connect to customer edge device, and they only run an IGP, e.g. OSPF or ISIS. They do not in any way run, or they're not aware of any BGP. So during your configurations, please do not configure BGP for these particular devices here. You only configure BGP, as we'll be seeing shortly. BGP is only configured between PE and PE devices, specifically multi-protocol BGP of VPN v4 address family. And the reason that is because we need to be able to transport this particular customer's prefixes from this location to this location. And the way we do that is by using MPBGP, because what happens is prefixes or routes will come to this PE device as IPv4, as a normal IPv4 prefixes, and then they will be converted into VPN v4 routes or prefixes. Then they will be able to be transported all the way to this PE here, and then arriving here as VPN v4 before they are sent to this CE. This provider edge device, what it does is that it converts them back to normal or standard IP routing or normal IPv4 prefixes, and then therefore they can be accepted by our customer edge device. Because remember, we said the customer edge routers do not handle MPLS directly, as due to that design, therefore you cannot advertise or transport customer prefixes from the PE to the CE um, in VPN v4 packet. They have to be converted back to IP or standard IPv4 packets before they can be accepted. That's how it works, and we'll be able to demonstrate that in our lab. Now, as you can see in red, I've indicated that where we have the PE devices, I have indicated that they are also known as label switched routers. So in the MPLS terminology, or based on MPLS, a provider device can also be called a label switch router or a transit router. And a provider edge device is also known as a label edge router. because it sits at the edge of our service provider network connecting to our customers. Now, depending on how traffic is flowing, if traffic is flowing in this direction, then this one becomes an ingress. It becomes an ingress label edge router, and this becomes an ingress label edge router. So if traffic is moving this direction, roles interchange, this becomes an ingress label edged router, and this becomes an egress label edged router. So depending on where traffic is flowing from, then you'll be able to establish whether this is an ingress label edge router or an egress label edge router. Another term that we need to know or talk about is VRF. VRF stands for virtual routing and forwarding. This enables our provider edge devices to be able to have multiple routing tables for each customer that you support. So if you're talking about L3 VPN, and that will be our main focus for this particular discussion, especially for this video. So if we're talking about L3 VPN, now we have two customers. They have the customers here are Bravo and Alpha, as you can see. So these two customers, they share the same provider edge devices at both ends. Okay. Now we need to find a way to have Bravo, for example, have its own routing table, and Alpha have its own routing table, but sharing the same physical device. What enables us to do that is the VRF or VPN instance, for those ones who are familiar with the Huawei terminologies. Now, another thing that we need to discuss is route distinguisher and route target. So route distinguisher is a 64-bit number. It's a 64-bit number that enables the separation or uniqueness of customer routes. For example, Bravo will have a route distinguisher, for example, in the format 1 colon, let's say 1030. If you combine CE10 and CE30 to get 1030. Sorry, that's not Bravo. That's not Bravo, but Alpha. So Bravo will have 1 1030, and then Alpha will have maybe 1 20 40 as route distinguisher. So this particular value here distinguishes or makes this customer to be unique. So when you're creating the VRF, this will enable that separation to take place. And in so doing, it will enable, once we've done the VRF, then we can be able to use overlapping IP address space, as you can clearly see on your screen. Another term is that works hand in hand with the route distinguisher is the route target. So route distinguisher makes custom routes unique. Route target is what enables you to control what you're exporting and importing, or from which VRF are you exporting routes from, and from which VRF are you from what, sorry, let me take that again. From what VRFs are you exporting routes to, and from what VRFs or VRF are you importing routes from? Now, assuming that again it's a 64-bit number, just like the route target. So assuming that we've decided for Bravo, we'll use again let's say assuming our AS number here is 100, and then Bravo's AS number is no, that's not, yeah, that's Bravo AS number is 1030, combining 10 and 30, and then for Alpha the AS number is not 1030, but rather the AS number is 2040. So let's say that we combine this and come up with the for Bravo we can come up with the route target in the format of 100 being our service provider AS number, and 1030 being the AS number of Bravo. And then down here for alpha, we can have 100 colon 2040. Okay, so this particular value will be used to import and export routes. So how it works is, if I am sending routes here, I'm exporting. Okay, and if I'm sending and if I'm sending routes from this PE to this PE, I'm exporting. So whatever this guy is exporting, he's importing, and whatever this guy is importing, he's exporting. Therefore, what enables us to be able to control that import and export is the route target, or in short, it's abbreviated as RT. Route distinguisher is abbreviated as RD. So uh, that is what I wanted to discuss about the terminologies. So it's important for you to know those ones because they will form the basis of our lab as we move forward. So the MPLS structure. So the MPLS label fields, as I said, the MPLS header itself is a 32-bit number that has the following fields. It has the label field, it has a traffic class field, bottom of the stack field, and the time to live. Now, the most important one are this one here, the label field, which is a 20-bit. Traffic class is 3 bits, and time to live is 8 bits. So bottom of the stack is just 1 bit. So combine this together, you get 32. Now, the label, as I said, is fixed. This is what gets assigned to customer routes, or not even customer routes alone, even within the MPLS service provider core. Prefixes are being are assigned a label just for identification to make packet switching faster. Now, when it comes to traffic class, formerly known as XP bits, this is what enables MPLS to be able to accommodate quality of service. As we spoke in the previous slides, QoS, for example, enables us to prioritize one traffic from the other. For example, you give different treatment to voice and video. You cannot give the same treatment to normal data, for example. So the values here are 0 all the way to 7, and 6 to 7 are reserved for network control. And 4, for example, is used for video. 5 is used for, I think, voice. And then when it comes to 0, this means there is no QoS. This is normal, or normal, no QoS. And then there is 1, which can be best effort. And then 2 is it can be, the next best thing after the next effort, I can say. So QoS is not our topic of discussion, so let me not digress. But basically, this traffic class is what enables MPLS to be able to support quality of service. Now, time to live is another important one, because this one, just like the TTL that we have in normal IP routing, it prevents loops, whereby it prevents packets from moving inside your network, your MPLS network, infinitely without stopping. So the time to live field is 8 bit, is again, it's 8 bits, and its sole purpose is to prevent loops. So that's done. The idea of label stacking. So we have outer and inner labels. So outer label is basically for transport, and then inner label is basically for service, and this is what identifies your VPN before routes. This is what identifies it is. So the transport part of it, or the outer label, is what enables, if I could pick our image here. So the transport is what enables label swapping. So if traffic hits this device, so the routes uh, yeah the routes are assigned labels. So this device here is responsible for pushing or adding label. Then it goes to this device, it swaps. So this device, it swaps. Remember, it's also known as a transit router. And then from here again, after swapping the outer label, the inner label remains. That particular prefix is or traffic again, or packet, not prefix. That packet is forwarded to PE05. Now, when it comes here, because PE05 is connected to directly to a provider edge, what PE05 does is what we call penultimate hop popping. Penultimate means second to last. So what it will do before it sends this packet downstream, it will remove the outer label and maintain the inner label. The inner label is maintained is because it has to be used to be able to identify which customer VRF uh, does this particular packet belong to. So when that packet comes to provider edge 6, it arrives here without the outer label, but before it's sent out, the inner label is also removed, and this particular packet is sent out as a normal IPv4 packet. Okay, I hope that was clear. So we can go back to our discussion. So basically, that's what happens there. So these other ones here are actually some of the benefits that you get. So allow me not to repeat in the interest of time. I would encourage you to find some time and be able to read about MPLS extensively and understand what it is and why we need it in our modern networks. Next one, how it works, how MPLS works. I believe we've already discussed about this in our previous slides, but it doesn't cause any harm to just repeat for a better understanding. So these three here are what we call MPLS label operations. So we have pushing, swapping, and popping. Now, label pushing is done at the ingress router, which is basically the provider edge device, which is also known as ingress label edge router, as we have discussed. Now, the ingress provider edge device assigns labels by classifying packets into forwarding equivalence classes known as fake. After you classify those packets, then packets that are classified into a fake are treated the same way. The next, label swapping, is done by the intermediate routers. So these ones here are the intermediate routers, which are called label switch routers. These are the intermediate routers. So intermediate router, intermediate provider router, also known as LSR or transit LSR, or transit router. Sorry, it's transit router. Swaps labels to avoid complex IP lookups, which enables us to enhance, which enables MPLS to enhance network performance. Now, the next operation is label popping. This one says here it's done at egress router because it's true, because the inner label is removed at the egress router, but PHP happens at the very last P device that connects to our provider edge device. That's where we have our PHP. So the egress provider edge router removes labels before forwarding packets using standard IP routing, because remember, our customer edge devices do not know anything about MPLS. They are MPLS unaware. So when it comes to the control plane, some of the protocols that MPLS is able to leverage are LDP for label assignment and distribution. Then we have RSVP, the extension of traffic engineering, which enables you to be able to do traffic or configure traffic engineering. And then, of course, we have segment routing. This is a topic of discussion that we can come up with a few series of videos to discuss about segment routing, because this is now what is replacing the normal MPLS TE. So we are moving away from MPLS TE to segment routing MPLS. Now, so we'll be able to discuss this at a later video, so let's not digress. But basically, that's what we have in terms of how MPLS works. All these will come. Well, all this will be able to be clear. It will make sense to you when we finally get into the lab and start the configuration. Applications and benefits. So common applications, we've already discussed this. So L3 VPNs. Layer 3 VPNs enable multiple customers to securely share the same network infrastructure. And isolated communication, this one here, where you have the overlapping IP space, like I showed you in our topology that we're using for the purposes of this video, because our lab has a different topology that we'll be able to use until we are done with this MPLS video series. Then we have L2 VPN, sorry. Layer 2 VPNs extend Ethernet services across wide area networks, supporting flexible connectivity options. And then we'll discuss about this in our lab. Traffic engineering, of course, this gives you as a network engineer the control or to be able to determine which path. Remember, path here can also be referred to as LSP, label switched path. So traffic engineering enables you to explicitly determine which path traffic is supposed to take from the source to the destination. And of course, as we may be aware by now, MPLS is used in a backbone transport and data centers, and because of the obvious reasons that we have discussed, it's used because it's able to use labels to do packet forwarding instead of IP routing, and what you get with that is fast and efficient packet forwarding. Basically, that's it. Again, I encourage you to read more about MPLS, because this particular video here is just it's just meant for us to lay I can say a basic and foundation of MPLS before we do the configuration. So apologies if I'm rushing through this. It's because at the beginning I said you need to have as part of the requirements or prerequisites, you need to have a basic understanding of MPLS. So benefits of MPLS. Some of these things in here have been repeated, but there's no harm in going back and discuss them again in a different context. So we have scalability and growth. So MPLS supports network scalability, efficiently managing growing traffic without performance loss. We can accommodate many customers within our service provider environment. There's secure communication isolation, where you can use virtual routing and forwarding ensures isolated and secure communication between different users or departments. I think I already showed you this where when we were discussing about VRFs and what it does. So VRFs, down here we have route distinguisher and route target. So basically, these are what ensures isolated and secure communications between different users or departments while using the same MPLS infrastructure. Quality of service is something we've already discussed. So quality of service prioritizes critical applications like voice and video. If you remember, we said voice uses the experimental bit number 5, and then video uses 4. So it prioritizes critical applications like voice and video for consistent performance during high traffic, and this ensures that your mission critical or important traffic is not interfered with, or it's given priority over other types of traffic. And of course, another thing that you get with MPLS is resiliency and fast convergence. MPLS enables rapid recovery from network failures, minimizing downtime. So if you remember, when we were discussing this particular topology here, so we assume that traffic is taking this path. Sorry, if I could pick our pen. Traffic is taking this path to go to this destination. Okay. And remember, we also discussed about LSP, label switched path. Basically, these are predetermined. Predetermined means already we have a few LSPs that are already established. In the event there's a failure here, this node here is out, let me say this link here is down, then therefore this particular path is broken. But not to worry, because since LSPs are predetermined, there's already another LSP that is established and is on standby, ready to be activated and to be used in the event that the primary one fails. So that's what you get with the MPLS. Resiliency, as you can see clearly, what you get there with MPLS is resiliency and fast convergence. So let's see MPLS in service provider and enterprise networks, specifically why it is used. Let's discuss this briefly. Now, number one, MPLS acts as the backbone for service provider networks, enabling scalable, reliable delivery of internet and VPN services. Remember, we talked about now we talked about resiliency and fast convergence. This is why MPLS is used. We can also use MPLS to connect enterprises. So assuming if I could go back to our topology, assuming that this is our enterprise here. This is our enterprise here. We say this was Uganda, and then there's another branch here in Kenya. But they don't have an infrastructure for them to be able to communicate with each other. So they come to us as a service provider, service provider, and then they leverage the use of our infrastructure all the way from Uganda to Kenya for this enterprise offices to be able to communicate with each other, and that is made possible by leveraging the use of MPLS. Moving forward, MPLS has advanced network features, and let's talk about it and say, and here you can see I've said MPLS supports traffic engineering, quality of service, and network segmentation, essential for modern applications. So this is very key. So this network segmentation or isolation, as we had discussed earlier, this one is very key, and this is where our VRFs come in. Okay, and then MPLS can be used in hybrid network architectures, of course. That goes without saying. So these are the benefits that we get with MPLS, and there are many other out there. Again, I encourage you to do a little bit of studies about that and get to know why MPLS is used in service provider and enterprise networks. Of course, you can use MPLS even if you are managing a very small network, but you will find it deployed in service provider and enterprise networks. Next. Now, we have come to the end of our brief introduction about MPLS. So from now here on, we'll purely be doing the lab. Now, the things that we will cover, we'll do MPLS, L2 VPN, and L3 VPN lab. The things that we'll cover here are, number one, we'll do we'll be able to configure or assign IP addresses to relevant interfaces configure loopbacks and IGP. And as I mentioned at the beginning of this video, we will be using SIS. In the interest of time, I will go ahead and configure this. I will go ahead and configure this, and then also do the configure. This is basically basic IP addressing, nothing more. This is something that you already know. And then now we will start our work or our lab by configuring ISIS, and then we go ahead and enable MPLS in the core, and then after that we configure MPBGP between provider edge routers, and the address family we will use is VPN v4, and I will be able to tell you why we're using VPN v4. Already I've discussed it in theory, but you will see it in practice. Then we will create customer VRFs or VPN instances. We'll do that particular configuration or customer VRFs on all the relevant PEs. And then we've discussed about route distinguisher and route target in theory, but now here we'll be able to see how they are put into practice. Then after configuring or creating VRFs, we'll attach customer interfaces to those VRFs, and then we'll establish PE to CE routing or peering, and here we'll use BGP. Of course, you can use ISIS or OSPF. The choice is yours. But the reason as to why we're using BGP is because we will not be able to, there will not be any need to do route redistribution or route import. Whereas in ISIS or OSPF, we'll be able to do redistribution, which could be complex, and it could be it will take time to do those configurations. So just for simplicity, we are deciding to go with BGP as PE to CE peering, and specifically this one here is IPv4, the normal IPv4 BGP that you know. So it's normal IPv4 address family. But for MPBGP, we are going to do VPN v4 address family. And then the configuration of a MPLS L2 VPN, specifically virtual private wired services, will involve one legacy configuration, basically how L2 VPN is, configured as per the exam blueprint, that is, and it will also involve one real world scenario where we'll be able to leverage the use of L2 VPN configuration to give one of our customer IPT services, and I will be able to show you how this is configured in real world. And then finally, we'll be able to tackle MPLS traffic engineering, where the protocol here is Resource Reservation Protocol Traffic Engineering, or RSVPTE in short. Then very lastly, we'll do the verification, be able to verify that our customers that are geographically separated are able to communicate with each other, and that we have full connectivity of our customers. So if I could take you back to our topology again, what we'll have to ensure is that this customer should be able to communicate with this customer, and this customer should be able to communicate with this customer. And this is for L3 VPN. So for L2 VPN, we will also do configuration of L2 VPN. And basically for L2 VPN, these particular devices here have to be in the same subnet. As you can see, these ones here are not in the same subnet, and they're able to communicate because they're communicating at layer 3. So this is L3 VPN, but this one here will be our L2 VPN. So we'll do those configuration and be able to have a better understanding of how MPLS is configured. So that's it for this video. Yeah, it was meant to be a very short video, and I would like to thank you so much for taking the time to be with me from the start to the end as I discussed MPLS in theory. Now our next video will be on now starting to configure MPLS on Cisco and Huawei devices, and specifically, these are the things that we will cover. So thank you so very much, and I am looking forward to seeing you in our next video. Bye for now.